We're doing more examples of using derivative shortcuts. So if we have f of x equals 1 over x squared, I could rewrite 1 over x squared. It's x to the second, you can see that, but it's underneath the fraction bar, so that's a negative 2. So now when I take the derivative, I'm going to multiply down. There's a 1 right here, so negative 2 times 1 is negative 2x, and then I'm going to subtract 1. Negative 2 minus 1 is a negative 3. So when I rewrite this, I'll say f prime of x equals, the negative 2 is in my numerator. You can imagine there's a 1 in my denominator. This x, because of the negative exponent, will be in the denominator, so this is negative 2 over x cubed. And you can see that I'm dividing by an x here. Just like we're missing one x each time. You subtract 1, you're really dividing by an x. For the next problem, I know that because we start having fractions when you starts to confuse people. So what if you have f of t equals 4t squared over 5? These aren't hard, they just look like they're going to be hard. You find your coefficient and just pull it off to the side. So this is really 4/5 times t squared. And then now you should be able to see you just multiply down and subtract 1. So we'll have f prime of t equals 2 times 4/5. That's a 2 over 1, so it's 8/5. Then you subtract 1 from your exponent, so t. So it could be 8/5 with the t written right here. A lot of people will write it in the numerator. For our next problem, what if you have f of x equals 2 divided by x? Well, if I rewrote that, that would be 2, and then my x is to the first power, but it's underneath, so 2x to the negative 1. When I take the derivative, I'm going to multiply down, negative 2x, and then I'm going to subtract 1. Negative 1 minus 1 is negative 2. So my f prime of x will equal, negative 2 is in the numerator, which puts a 1 in the denominator. The x has the negative exponent, so it goes in the denominator as well. So negative 2 over x squared. I started with an x to the first in the denominator. I now have x squared. For our next problem, we have y equals 2 square root of x. If I rewrote that, this is a square root, and it's x to the first power, so this is 2x to the 1/2. Now when I multiply down, 1/2 times 2 is 1 times x, and I'm going to subtract 1, so minus 2/2. That's to the negative 1/2 power. So I would say y prime, or dy dx, equals, the 1 is in my numerator, this x is in my denominator. It's to the first power, but we're taking the square root. Now some things are interesting to note right here. This is quadratic, and quadratic functions are continuous and differentiable, so you can see that everything's fine with this derivative. There's nothing that will make this derivative and this original function discontinuous, and there's nothing that will make the derivative discontinuous. If you look at this one, we're starting with an x in the denominator. So our function is not continuous at 0. You'll notice our derivative isn't as well. And remember that continuity is a requirement for differentiability. So if it's not continuous at a point, it won't be differentiable at a point. This is a different kind of example. It is continuous at 0. This is just 2 times the square root function. Now it's one-sided continuity, because if you take the square root function, the scale is twice as big, but it's continuous at 0. Over here, you can tell that it is not differentiable at 0. If I plug 0 into the denominator here, I get 1 divided by something really, really small, which is really big. It's going to head towards infinity. And if you think about the slopes of the tangent lines, it's approaching vertical, so your tangent line doesn't really, or rather your derivative doesn't really exist at that point. So that's an interesting case. Okay, our next example would be y equals 1 over 2, and then I'm going to do the cube root of x squared to make sure we understand all of our exponent parts. So if I rewrote this, I'm going to say this is 1/2. I'm just pulling the coefficient off. Then my x is squared with the cube root, and it's underneath the fraction bar to the negative 2/3. So when I do this derivative, I will take my negative 2/3, multiply it down. You can cancel your 2's. Remember, you multiply straight across, so it's 2/6, or cancel the 2's, 1/3, and we have our negative. So it's negative 1/3 x, and then I'm going to subtract 1. Negative 2/3 minus 3/3, that's our 1, is to the negative 5/3. So if I rewrote this one, it'll be y prime equals, the 1 is in the numerator, the 3 is in the denominator. My x is in the denominator because of the negative exponent, so negative 1 over 3. My x is being cubed, and I'm sorry, to the 5th power, and a cube root. It's underneath because of the negative exponent. So again, cube root, 5th power, under the fraction bar. Our next two examples are very similar, but I wanted to focus on them for a minute. What if you have y equals 5 over 2x cubed, or y equals 5 over 2 and then just the x's cubed? If I rewrite these, they're going to look very different. The coefficient for this one is 5 over 8 because you have to actually cube it first, and that's if I'm choosing to do the power rule. So this would be 5/8 x to the negative 3. This one, the x is cubed, but the 2 isn't. So this one would be 5/2 x to the negative 3. So be very careful with parentheses. If you're just going to use the power rule, you need to get rid of all your parentheses. So now I multiply down. That's a negative 15/8. Remember, negative 3 over 1. Multiply straight across. X to the negative 4. For this one, it's a negative 15/2 x to the negative 4. So I have y prime equals negative 15 over 8x to the 4th. For this problem, I have y prime equals negative 15 over 2x to the 4th. So the parentheses definitely matter. You need to make sure to get rid of the parentheses before you start using the power rule.